Hello, today I'll be talking to you about a project I've been working on with my advisor, Dr. Xing Chu, about combating the curse of dimensionality in multidimensional functional data analysis. So I'll begin with a brief overview of functional data analysis, and particularly the functional representation problem, talk about how the curse of dimensionality creeps in here, then give an outline of our proposed methodology to combat this problem, and then give a brief outline of a real data application where we use our methodology to analyze DTI data for predicting traumatic brain injury. So functional data analysis is concerned with the analysis of collections of smooth functions, which are considered as realizations of a random function or random field, which we denote as F. A random function is a measurable function with values in a separable Hilbert space. For many applications, this space is the set of L2 functions over some domain M, which is a compact subset of D-dimensional Euclidean space. And we typically only have access to a random sample of discrete noisy observations of the underlying field, assumed to follow the statistical model here. So when I talk about functional representation, I'm referring to the process of estimating the underlying smooth realizations, Fi hat, from the discrete data that we actually observe. This is the first step in many FDA pipelines. And the downstream tasks of interest, whether it be prediction, functional principal components analysis, or hypothesis testing, are defined with respect to these representations. This is typically accomplished with some type of basis expansion. So if we let V be the span of some set of basis functions and J a non-negative penalty functional, the ith representation can be defined as the solution to this penalized least squares optimization problem here. So where does the curse of dimensionality come in? Two places. One is known as statistical curse, says that a non-parametric estimator of a smooth function requires a number of observations exponential, and D if you want to retain the same mean squared error. There's also the computational curse, which is what we'll be focusing on here, which is the exponential explosion in the computational domain as D increases. And this can be referring to computational time or the number of parameters in a computational model. Instance of the latter is the number of basis functions in a tensor product basis. So how has this been handled in the past? Typically impose some sort of structural constraints on the functions that you're estimating. This is where you get things like additive models, single index models, and semi-parametric regression. Unfortunately, many of these commonly used structural constraints are not expressive enough to model complex patterns encountered in many real multidimensional functional data sets. So our proposed solution is to investigate another structural assumption that simultaneously permits a richer model space while not suffering from an exponential increase in the parameter space. So this structure we call marginal product functions, and I'll give an outline of it here. So if we assume that our domain can be decomposed into the product of D marginal domains, each of which is a compact subset of some Euclidean space. The rank one multidimensional function is the product of D marginal functions, where each of those marginal functions are L2 over the corresponding marginal domain. Then a rank K function is just a linear combination of K independent rank one functions. So modeling with this type of structure has been considered in a variety of contexts and gone under different names, just sums of separable functions and low rank tensor functions. So it's not a new structure. This is a new kind of application area for it. So one particularly attractive feature of this structure for our purposes is that it possesses a universal approximation property. So if we let phi d be a complete basis system for the set of L2 functions over each marginal domain, we can define the marginal product function approximation space as a set of functions that are within the span of this here, where each of the marginal functions are an m-dimensional expansion over the corresponding marginal basis system. And under some conditions on the distribution of the random function and relative growth of the marginal and global ranks M and K respectively, we can prove that there's an element in our approximation space that is arbitrarily small expected L2 error with F. So in light of this, we would like to construct a set of smooth marginal product functions that are in some sense optimally adapted to the distribution of F, and that they minimize this functional here, where pen is some penalty functional promotes smooth solutions. We propose a method to estimate this guy from discretely observed realizations of F that we actually get in practice. So the statistical model for our observed data, assume that we have a random sample of n realizations that are observed on a common grid. So this data can be organized into a D+1 mode tensor, which we denote Y, where each element of the tensor is assumed to follow the statistical model, which is the same statistical model, standard statistical model in FDA from the first slide. So in order to incorporate penalization, we looked at the separable roughness penalties to promote smoothness in the basis functions. So this has the form given here, where lambda d is penalization strength and LD is a linear partial differential operator, which encodes the notion of smoothness along each of the marginal basis functions here. We also incorporated sparsity using an L1 penalty on our coefficients. So that as we allow solutions where the ith representation has a non-zero contribution from some subset of the k total basis functions. So how do we actually compute this in practice? Under the data transformation given here, so it's the sequential d-mode multiplications of our raw data tensor y with these matrices UD. I don't have time to go into what these matrices are, but they can be computed from the data. The empirical counterpart to the optimization problem is equivalent to this optimization problem here, where this is kind of the least squares component here. This is the roughness-based regularization, and this is the sparsity-based regularization. And TD, I don't have time here to go through the derivation of it, but it can be determined by transformation of the linear differential operator into this coordinate space of the C utilities, which are our optimization variables. And you can prove that the optimal marginal basis functions, which are defined here, are determined using the transformations of the solutions to this optimization problem. So we have data transformation, solve the optimization problem, and kind of invert those solutions to obtain the solutions back in the original coordinate space. Why this is helpful is that for this optimization problem, we were able to derive a fast parallelizable algorithm to solve it using a combination, using block coordinate descent and alternating direction method of multipliers technique. So I'm going to run through a few key properties of the PROS framework before I run through the real data application. When compared to a tensor product basis system, we no longer have exponential increase in the number of basis functions. When compared to semi-parametric models, we have this universal approximation property versus potentially overly restrictive model space. And a more subtle point is that we're controlling the dimension of the optimization problem. So the tensor that we're actually decomposing, which is G, is a compression of the raw data tensor, whose dimension is determined by the ranks of the marginal basis systems, which is a parameter that is user specified. So for our real data application, we looked at DTI for traumatic brain injury. Our data set consisted of 25 traumatic brain injury patients and 25 age-matched healthy controls. They were all scanned at the University of Rochester Medical Imaging Center. Diffusion tensor imaging was applied to the diffusion-weighted MRI and used to compute a scalar measure of diffusion called the fractional anisotropy. And we leveraged proposed methodology to perform a multidimensional functional data analysis of the diffusion fields. So we evaluated our representations in two tasks. First was a prediction task, where we simply trained a classifier on the coefficient vectors, so the coordinates of the representations with respect to the learned marginal basis system. We also defined a more kind of functional task, which is these data-driven ROIs. So first, you can define informative basis functions as those associated with coefficients deemed most important by the classification model for the prediction task. And then the region of interest can be defined as the spatial regions in the brain where the values of the informative basis functions are extreme. So they're above or below 99.5% quantiles. So for the prediction task, it's the confusion matrix of the lead one out cross validation results. The accuracy, precision, and recall were all hovered around the 0.9 region, which is a very strong result for predicting traumatic brain injury from diffusion data. So here's some of the data-driven ROIs we were able to recover. So the green, red, and blue correspond to the three-dimensional informative basis functions. So in the top figure here, this region of interest is concentrated in an area called the middle cerebellar peduncle. It's known to be involved in motor processing. In the bottom, they're in a region called the superior longitudinal fasciculus, which is involved in motor processing as well as language processing. But the take-home message here is that each of these regions are known to be affected in TBI from anatomical studies by radiologists. So we were able to, in a completely data-driven way, determine regions of the brain which are affected by the disease that we're interested in. So that's it. Thank you for coming and listening. Anything you wish to me to elaborate on, or any questions you have or follow up, or I'd be happy to answer. Thank you.